Hello, welcome to Lesson 2, Section 2, CQRS. Let's review what we learned in this section. Firstly, we will look at what CQRS is. CQRS stands for Command and Query Responsibility Segregation. It is an architectural pattern, although not a top-level pattern, that states we should separate our read side from the write side. On one side, we send comments to our system, and those comments change the state of our application. And separately, from our read side, we access things like reporting, or if we need to read some information, we also access it from read side. The goal of this separation is that by applying CQRS, we can prevent the changes from read side to creep into write side. Usually, we have different requirements for the read side and write side, such as we need different kind of reports. Just because we need a different kind of report, we shouldn't change our write side that recites our main logic. We will see more about that. In CQRS, we use aggregates. A good way to apply aggregates is actor model. We will briefly see what an actor model is. Next, we will see about akka.net, which is an implementation of actor model in .NET world. We will see its relevant features and see an overview of it. Finally, we will go through a preliminary design of a banking application that allows us to transfer money from one account to another, and we will see how we can handle the transaction boundaries correctly and how we can handle concurrency problems. CQRS overview. In the classical approach, we have command and queries unified into one single model. That is, if you use an ORM, you typically create your entities where you read and write to the same tables. If a report is required, you again rely on those tables. However, if your report side or read side requires complex reports, then you have to generate many complex join queries, or you have to asynchronously create a denormalized table. This denormalized table eventually has led to command and query segregation. In command and query segregation, we have the write sides of the command and the read side of the queries are separated. If I were to give you an example of a command and query segregation, that is, suppose that you want to make a money transfer, a transfer command is sent to the command side. It is processed from that side only. And if I want to know what is the total amount of a particular person has in its balance, or if I want to know total balance of all accounts, then I will go to the query side. This enables me to have smaller and isolated parts of my application, and command and query side can evolve independently. It also has benefits like asynchronity, and my read side can scale independently of the write side. And in the classical definition of command and query, we can say that a command is something that alters a state, and it doesn't return any state. Having said that, there are actually valid implementations that a command can return something like a primary key, something that is created, or an outcome if the command is rejected. Some people implement the command in a completely asynchronous way, and some people prefer to return simple things like if the command has succeeded or if it created something, we can return that created thing's identity. I'm personally in the second camp. I prefer my commands can return simple and elementary things like the primary keys or a rejection message. On the other hand, the query just returns the data and it never ever alters the state. Actually, in CQRS, it is forbidden that command side accesses to the query side, because if you try to access from command side to query side, then the whole motivation of CQRS is defeated. That is, we do not want the read side implementation to leak into the command side. Remember, that enables us a lean and a focused domain model. Again, here in this slide, we see two implementations. On the left side, we see the classical layered approach, that data flows between the layers from presentation, application, domain, and infrastructure and returns back. On the right-hand side, we see a typical CQRS implementation, where the application and the domain is exposed to the commands, and whereas for the query and read side, we only expose our DTOs and data access. And this enables us, the domain, and the read side evolve independently without interacting with each other. How about the functional world? In a typical implementation in the functional world is that we have an actor or something like a command handler, and we have an initial state. Suppose that we have a bank account, and this bank account has a state like balance. And if we send a command like make a transfer from this account to that account, and this is combined with the state, the actor or the command handler or the aggregate first persists, then applies, and finally publishes an event. By event, I refer to something like $500 has been deduced from this account. Once this event is generated and persisted, it is sent to the event handler and combined with the state. Suppose that our state states that our balance was 1,000. Then this event will combine with the state and it will generate a new state. In this case, our balance will reduce to the state. Our balance will be reduced to 500 from 1,000, and this new state will be used by the subsequent commands. What if there is no enough balance in the first place? In this case, our command handler will reject the command and may publish an event about the rejection. If we come to event sourcing, actually, as we mentioned, from the command stack, we generate a bunch of events, and these events allow us to trace anything within our application. And finally, they are sent to the read data store. By read data store, we mean any kind of database like PostgreSQL, SQL Server, MongoDB. What actually happens is, once we have acquired the log of events, the next thing we will have is a process that scans the log of events and that generates denormalized data and whatever report we require. And basically, since we have the trace of the events, we can generate as many reports as we can, and these reports can be very complicated depending on the requirements. Since we are generating reports for denormalized data, this read side allows us to get rid of complex joins. We will see an example about this. And let's review events and commands. Basically, from a CQRS point of view, they are both messages. That is, first of all, a command is directed at one handler, and it can be rejected by the system or by receiver. So a command is something that we ask for. Also, a command can fail while it's being executed by some handler. So there's a possibility that some service that is required to execute this command can fail. And generally, a command doesn't generally trespass the boundaries of a given bounded context. And finally, a command's naming should describe something to be done. Whereas an event can't be rejected or canceled by a system, because an event represents that has something already happened. So if you have transferred your money transferred is an event. This cannot be rejected or canceled. It can be undone, but cannot be rejected. And an event eventually can generate other events as well. An event can be listened by other subscribers outside of the bounded context. And finally, an event can be an idempotent. This is an important concept. That is, once a component receives an event and receives the same event second time, it may ignore the first event. Actually, the same can be told by a command too. So a command can also be idempotent. Idempotency can be very important on a failure-prone systems. That is, if you send a message to some other component and you're not sure if that message has been received, you may want to retry that message. But if your message is not idempotent, in that case you may duplicate the side effect. In functional point of view, idempotency can be represented as, if an f function takes itself as a parameter, then it would yield the same function. Now let's talk about event sourcing a little bit more. Suppose that we have a banking system. We have commands like reserve amount, add amount, commit reservation, and each of these accounts receive these commands and then generate a relevant event. And as a result, what we persist, unlike the classical way of CRUD applications that we use some sort of ORM in the account itself, we only save the event itself. This has several benefits. That is, we never lose any information among our system. Even we keep the previous values of our data. For example, if we were designing our application a classical way, that with a table of an account and a balance, and if our balance constantly changes, we will never know what the previous value of the balance is. So event sourcing is a way to not to lose any data. And whenever we want to rehydrate the account, what we do is that since we have already recorded all the events that are associated with that account, we just replay those events. However, come to think of a scenario that we can have thousands of events that are associated with the given account. In order to solve this problem, occasionally we generate snapshots. Snapshots represent the full-fledged state of the object, and after the snapshot has been persisted, we continue to persist the events. And interchangeably, we can use snapshots or events for hydration, depending on our requirements. That way, we are able to solve the performance problem that is due to accumulation of hundreds or thousands of events.